What we're still doing, we're looking at examples of the greedy algorithm design way of thinking, and my hope by now is that you have got the essence of how to design a greedy algorithm. And what we are going to look at today are more advanced examples of greedy design. And I hope by now you realize that your only way to be good in algorithm design is to see many examples and work out as many problems as you can. I know you could be short on time in regarding that, but that will be your challenge for taking this course. The reason why I'm saying that, because if you noticed, every problem we have seen up to now, whether in divide and conquer or in greedy, every problem has its own kind of idea. The underlying technique might be the same, but when you come to apply it to design a solution or an algorithm, each one is quite different from the other. Okay, so seeing as many examples as you can, and solving as many problems as your time allow, is your only way to be good in algorithm design. Seeing the lecture, attending the tutorials online, or seeing the tutorial videos is not enough. You have to solve problems on your own. That's the only way you can really learn algorithm design. While I'm giving you the basic principles, you still have the challenge of acquiring the skill of designing an algorithm on your own. And the only way to do that is by doing it a lot. So I would advise you, for example, to check Geeks for Geeks. Very popular website, has tons of problems, and I got some of my problems in the lectures and in the practice assignments from there, and also from other sources. But the nice thing about Geeks for Geeks, although I'm not really advertising for the website, but you have to give it credit that it has managed to compile a huge list of problems. So saying that, let's actually start the lecture today by seeing the following example. The problem we're going to look at now is called the knapsack problem. The problem goes like this. Suppose you have a bag of a maximum weight. So the bag can only hold up to a maximum weight. In this case, as you see here, 15 kilos. Suppose you have a set of items. Each item has a weight and some monetary value. You see here a number of items. There's 5 of them. 12 kilos worth $4, 1 kilo worth $2, 4 kilos worth $10, and another 1 kilo worth $1, and 2 kilos worth $2. The challenge here is to collect from the items, to put in the bag, the most valuable combination of items. For example, if I pick the 12 kilograms and put them in the bag, I have just made $4, or just made a profit of $4. But then I'm only left with 3 kilos left, free in the bag. So I could take the 2 kilos, and that will make my total $6, and my weight 14 kilos, and that gives me 1 kilo left. So I can take the 1 kilogram with $1 value, or the 1 kilogram with $2 values. So I will pick the 1 kilogram with $2 values. That's one possible combination. Okay? The 12 kilos, the 2 kilos, and the 1 kilo who's worth $2. And that will give me a sum of 4 plus 2, 6, plus 2, 8. I could also do something else. I could take the $10 worth 4 kilos, but then I cannot put the 12 kilos in the bag because the maximum weight will be exceeded, because the weight will be 16 kilos while the bag takes 15 kilos. So I could take the 4 kilograms that is worth $10, and then I will put on the top of that 2 kilograms who are worth $2, so that makes $12 and 6 kilograms. And then I can grab the other 2 kilos, one for $1 and another one for $2. So my profit here is going to be $10 plus $1, that's 11, plus $2, that's 13, plus another $2, that's 15. So that's $15. It's more than what I tried to combine in the first attempt. Now, this is the idea here. We have a bag, it has a maximum weight, we have items, there could be many of them. The weights and the values could change from one instance to another. So for any specific given set of inputs, we would like to find the optimal solution, which will enable us to fill as much as we can from the bag weight and to make as much money as possible. So basically we would like to maximize the profit, and this is really our goal here. We don't really care if we minimize the weight or not, but we really would like to maximize the profit. And this is the knapsack problem. Very classical, has many applications. I know it looks a bit naive, but actually I will show you shortly another variation of it. This is used in shipping industry. This has applications in manufacturing. It has application in even routing of packets sometimes, depending on the protocol. So the idea is that you have a payload for every piece of information that goes in a packet, and there could also be assigned a monetary value, and this is typically in systems that enforce, or protocols that enforce, some kind of a quality of service. So it has many instantiations in different fields. Okay, there are two variations of the knapsack problem. This is what's called the 1-0 knapsack, which means either you take an item or you don't take an item. So either you take, if you look at the figure at the bottom left, the 4 kilos, or you don't take the 4 kilos. Okay, now greedy algorithm design cannot solve this one optimally. Okay, and we will talk about that shortly. But there is another variation of the knapsack which greedy can solve optimally, which is the fractional knapsack. Now, in the fractional knapsack version of the problem, you can take a fraction of an item. Okay, you can take part of an item. Where can you see an example of this? If you look at the figure at the bottom right, you see the same problem but in a different incarnation. What you have here, instead of solid blocks of weights, you have liquids, and you are going to take from each one of the bottles enough to fill in your container, which is going to be another bottle that doesn't show up here. So actually these bottles are labeled items from item 1 to item 5. This is what you fill in from. This is not your container that you're trying to fill. This is containing the liquid that you're going to take from. Now in this version, if you look at the first one, which is item 1, it has 4 milliliters that is worth $12. You can take only 1 milliliter, so you can take a fraction of the content. Okay, now, or in the 8 milliliters, you can take 2 out of the 8 milliliters, and it goes like this. Okay, so in the case that you can slice through an item or take a part of an item, we're going to call that the fractional knapsack problem. Okay, which is different from the 1-0 knapsack problem, because in the 1-0 either you take it or you don't take it. Here you can take a fraction. Now, before I show you the algorithm design, let me refresh your memory with the greedy approach. We said that the greedy approach is quite simple. There are 2 components to the greedy approach which you have to come up with. What we call the configurations, which is a fancy name for the choices that you're going to pick from. And an objective function, which is some kind of a mathematical function that enables you to pick from the choices in front of you. So you could sort the choices like we have seen with Crossco, and then, or the input data, and then pick the one that you believe is the best one to pick at the current time. This could be using, if it's a simple objective function, minimum, maximum, and so on, okay? But you could develop any kind of objective function. The point with greedy, again, is that, as the slide I have shown you before demonstrate, that you continuously pick from the inputs until the inputs are done. So you have to model the problem this way, okay? This is what I was referring to. You have to model it this way, which means you have to imagine that you have your inputs ready, you have an objective function that's going to pick one of them, and when you pick one of them, that one disappears from your input list, and ultimately you keep running the objective function on the available inputs until there is no more available inputs, and then you're done, okay? So going back to the objective function, we saw most of the greedy algorithms that you'll come across, you will be surprised by how simple objective function is. Why? Because we're being greedy, so there's nothing really super sophisticated about it, okay? Why they pick the minimum, the maximum, the shortest, as I mentioned before, the tallest, the heaviest, the most precious, okay? So it's going to be, again, the maximum. But we could develop more, sophisticated objective functions if you like, and you will see one shortly, okay? Now, regarding the configuration, and this is really what maybe some students, when they start to learn greedy, will find a bit challenging. You have to organize the data so it is in the form of a configuration, or basically in the form of an input list, okay? So for example, if you go back to Crossco, if you like, and if you think of what did we do, we actually grabbed all the edges from the graph, and we considered this as my input list to the objective function, okay? If you look at the graph as a graph and you try to run design a greedy algorithm on it right away without having this list, without having this configuration, it becomes challenging because you don't know where to go, which one to pick. But we managed to or the Crossco algorithm managed to do that very simply by saying, okay, here's the input graph, I'm going to extract all the edges, so now the graph is just a set of vertices, and I have the edges on the side, I will sort them, and then I will pick the smallest one first, put it back into the graph, okay? So what this exercise I was just describing is doing is basically enable you to think in a greedy way by processing the edges as a configuration or as a list of items, okay? So before we start seeing the examples, let's go over the steps. I've tried here to formulate it in terms of steps. So whenever you think you get a question like design a greedy algorithm to so and so, and you should be able to do that in a systematic way. Step number 1, state your input configuration. Okay, what is your input? Step number 2, state your goal. What are you trying to achieve? Okay, based on your goal, you will develop an objective function. Okay, and then step number 4 and 5 are trivial. You apply your objective function on the available input on configuration, and step number 5, you keep doing step number 4 until you're done. Okay, now again, as a word of caution, if you cannot formulate it this way, you're not doing greedy. Okay, you're not doing greedy. So you have to have configurations, you have to have a goal, you have to have an objective function based on the goal or trying to achieve the goal, and when you apply an objective function, your data size should reduce. Okay, it should reduce by 1 or n or whatever, but it should reduce. Okay, so if you're not doing it as I'm describing, let's say for example in step number 4 or 5, when you apply the objective function, the data is not reduced, but at the end, ultimately, when you reach some state, you say you're done, but you haven't reduced the input space, then you're not really doing greedy. Okay, this is the merit of greedy, is that you have to be reducing the input space as you keep running the objective function or passing the data to the objective function so that it picks one of them. Now, in the case of the knapsack problem, I think it's very clear, what is the configuration. The configuration is the set of items I'm going to take from, which is these, blocks that has monetary values, okay? So I have showed you before steps you go about in creating a greedy algorithm. Step number one, you have to state or come up with the configuration, your input, and in this case, it's very visible, it's very clear, it's going to be my items. So I have here input is the set S of n items, where each item is having some positive weight and some positive benefit, okay? I'm just trying to be a little bit formal here by saying that it's positive benefit and positive weight, but obviously this is a common sense. Now, one note here is that I will assume that I have one instance of each item. There are variations of the knapsack problem. I've already discussed with you one way to classify knapsack problems, whether it's 1, 0 or fractional. There is another way actually to classify knapsack problems, which is whether the set of items you're picking from are infinite or they are unique. So here I'm working with the version that it says it's actually unique in the sense that I have a fixed set of inputs I'm going to work with, okay? And the other variation, you have unlimited supply of inputs, okay? So it's not a set of n items, it's going to be a set of infinite number of items, okay? It makes a little bit difference for us because obviously we will come with a different solution if we have an infinite set of items, because if we know which one is really the golden item that we should stick to and keep adding into the bag, then all the other items are discarded. But if you have one instance of each item, once you collect an item or finish an item, whether you finish it by taking the whole of it or you finish it by taking fractions of it, okay, so if an item can be divided, say, into 10 fractions, and you consume all the 10 fractions and you still have space in the bag, then you have to go and consider other items, okay? So anyway, what we're looking at here is one instance of an item. Now, my goal, we already, this is the second step. We said you first define the input and then say what are you trying to achieve before jumping to the objective function. So step number 2 is the goal. I would like to choose items with maximum total benefit, but with weight is W or less than W. Okay. So again, this is straightforward from the problem statement. Now, we're going to look at the fractional knapsack problem, because fractional knapsack problem is solvable optimally by the greedy approach, and because it has this interesting way of formulating an objective function. So in the case of the objective function for a fractional knapsack problem, well, let's think about it, okay? The issue is I would like to pick the most valuable, right? Because if I always pick the most valuable in front of me, or what's left from the configuration, if I pick the most valuable, then, and I continuously do that, so I will pick always the most valuable, and then second most valuable, and then third most valuable. For sure, I will end up with the most valuable content in the bag. Because if I continuously pick the most precious thing I could pick, there is no way I'm not generating an optimal solution, because an optimal solution means there is something more precious. But if I'm actually picking always the most precious, the most valuable, then I will generate an optimal solution. Okay. Now the question is, if this is a fractional knapsack problem, how can we find how precious a fraction is? Okay, and there's a very straightforward approach we can do that. If I divide the weight by the value, then I will know the value of each fraction. Let me give you an example. Let's say I have an item whose weight is 10 kilos and its value is $20. So 10 kilos, $20. Well, that means that every kilo is worth $2, right? If we have 10 kilos and $20, so every kilo is worth $2. So I'm gonna divide the price or the value by the weight. Okay? I think I have said it the other way around. If I did, I'm sorry, I meant the price by the weight. Now, if I have, let's compare this to 10 kilos, that is worth $10. So the weight of the value of 1 kilo now is $1. So I have two items. They are of the same weight, 10 kilos. But one of them, a kilo of one of them is worth $2, and another one, the kilo of one of them is worth $2. So that second one is more valuable. It's more precious. So if I only have these two, I should pick from the second one, because it's more precious. So if I would like to talk about my objective function, I'm going to do the following. I'm going to say I would like to maximize the following summation. If you look at the term inside the summation, it says x of I, where x is the value of the item, divided by weight of I. Okay, so it's the price or the value divided by the weight will give me the value of a fractional unit of the item. And I would like to do that for all items. Okay, so I would like to maximize this summation. Okay, I hope now your math is coming to the rescue, because this is a function I'm trying to maximize. This is not a function I'm solving. Okay, I'm trying to maximize that. In other words, there are many variations of, or many instantiations of this formula, the summation of I belong to S, B of I multiplied by X of I divided by W of I. There are many instantiations of this summation, and I would like to pick, or I'm going to use the instantiation that maximizes my total sum. Okay, under the constraint that my total weight is going to be less than W, obviously. Okay, so we need to avoid exceeding the size of the bag. So let's apply what we just discussed on a specific instantiation of the fractional knapsack problem. Let's say we have a bag of 15 kilos maximum weight, and we have these items with the weight of the item and the price or value of each item printed as you see on the item itself in the leftmost image. Now, you see we have 9 kilos for $10, 12 kilos for $7, 2 kilos for $1, 7 kilos for $3, and 5 kilos for $2. We said that our strategy is going to be, we are going to maximize our gain by considering most valuable items first, and we are going to take fractions of each item, so we calculate the value of each unit item, and in this case it's going to be 1 kilo. So I divide the $10 by 9 kilos, I get the information that every kilo is worth $1.11. I divide 7 by 12, I get 0.58, and so on. And then I sort my findings, or my calculated weight per unit, value per unit, and I have the most valuable item first. That would be step number 4 in our design of the algorithm. Now, in step number 5, what we are going to do is we're going to apply our objective function, or select using our objective function to be more specific. So we consider the most valuable items first. So I will consider the one on the top of the list, which is 9 kilos for $10, since it has the highest value per unit. I will add that to my bag. That's what you see as step number 1 in the rightmost figure. So now I fill the bag, which has a maximum weight of 15 kilos, with 9 kilos. I next move on to the next item in my list. So I'm basically again listing them by most precious, second most precious, third most precious, and so on. So I have to consider now the one whose value of 1 kilo is $0.58, which is the 12 kilos and $7 item. So because that will make me exceed my total weight, which is 15 kilos, because the total now is going to be 21 kilos. If I add this one, I cannot add it. So I'm not going to add it to the bag. I consider the next one in terms of being valuable, which is the 2 kilos for $1. I will add it to the bag because 1 kilo there is worth $0.5, which is the third most valuable item I have. So I have to add that one. And then now my weight is standing at 11 kilos and my gain is standing at $11. I move on to the fourth item, and this is 7 kilos, so I cannot add it because I will exceed the maximum weight. I already have 11 kilos. If I add that one, it's going to be 18 kilos. It doesn't make sense because I can only add up to 15 kilos. The same thing for the fifth item for 5 kilos and $2. And consequently, the items I add to my knapsack to gain the highest value possible is the first item and the third item in my ordered list of items by value. Here is another instantiation of the same problem except with liquid items. So each item is stored in a bottle. As you see here, we have 5 items, 5 bottles, each item in a bottle, and we're given for every item the weight, or it could be the volume, of the item. Here we're given the weight and the benefit of the total weight. So for item number 1, I have 4 milliliters, and the benefit is $12, which means that 1 milliliter is worth $3. I'm just dividing 12 by 4. The second item, it's 8 milliliters, and its value is $32. So I divide 32 by 8, I get $4 per 1 milliliter of item 2. And this goes like that for the rest. Okay? If you look at the values, obviously item number 5 is extremely valuable compared to the rest, because I have 1 milliliter of it and it's worth $50. So if I divide 50 by 1, then the benefit is 50. Okay? Now, applying the same way of thinking, if I'm trying to fill a bottle that's 10 milliliters, so I will consider the relative, or the value per unit volume here, or per unit weight if you like. So 50 obviously I need to include, so I will include 1 milliliter of item 5, and my gain is $50. And then I will include 2 milliliters of item 3, because item 3 is the second most valuable, where 1 milliliter is worth $20. So I include two of them. This is the maximum I include because I only have 2 of them. Okay, so it's 2 milliliters there. And then the fourth item I will consider being my third most valuable liquid I have here. As you see, each milliliter of item number 4 is worth $5, so it's the third most precious liquid here. So I will include as many as I can. So I will include all of it, 6 milliliters of item 4, and finally I have 1 left, so I will include 1 milliliter from item 2. Okay. Now, this is just another incarnation where I'm basically repeating my solution to the previous slide, but in terms of liquids and bottles. And we could use the same way of thinking to solve many similar problems as previously mentioned, that could be modeled as the knapsack. So this might sound like a bit of a funny problem, or a somewhat childish problem, like you got this bag and you're trying to fill. But actually the nice thing about it is if this is something you should learn about algorithms. If you have a very, very difficult problem to describe and you can model it using something that is quite simple and intuitive to understand, then it's much better, because the solution for the simple and intuitive problem will also be the same solution for the more complex wording of the problem. So I could give you like an instantiation of the same knapsack idea, but in very complex words. For example, it could be like what you're trying to fill is a container, and you have these shipping boxes, and the shipping boxes have items in them, and then I can tell you either you include the box or you don't include it, or that would be like a 1-0 knapsack, or you could open the box and you can pick some items and regroup your box contained items into the container. And that would be like the fractional knapsack problem, So that will take way more effort to explain and model, while with the knapsack idea, which just means a bag and a bunch of items, it just much simpler to visualize and understand. Okay, so the knapsack actually is not just one problem. It's you could think of it as a class of describes a class of problems that happens or to exist in many fields and specializations. Okay, so I hope the idea is clear to you after these two examples. Now, we need to consider our claim that the fractional knapsack can be solved optimally by a greedy approach. Okay? Now, why this is an issue? You see, the problem with greedy algorithms, it is generally not easy to prove that the solution you arrive to is optimal, is the best possible solution. There could be another better solution that you cannot reach to by thinking in a greedy way, because that other solution requires some more in-depth thinking, strategic thinking, by not just considering the alternatives in front of you at a specific moment, but what will happen in the future. This will become clear as an idea when we see dynamic programming. That's number one. Number two, when we actually pick one choice from the set of choices we have in a greedy algorithm, we can't undo. We can't go back. After we pick it, we're stuck. Okay? Like we cannot undo our pick. And we have seen in the previous lecture with the example of the monetary units. I had this example with some fictitious monetary system called the crons that you could be forced using a greedy approach, because this is how greedy works, to pick the monetary value that will increase the number of coins that you're going to use to represent your target total sum. So the notion that a greedy algorithm generates an optimal solution by itself is not a trivial exercise. You could always, in most cases actually, I would say you could always come with, in a straightforward way, with a greedy algorithm to any given problem. Why? Because it's actually a bit trivial. You're not really thinking deep into the problem. You're just saying, okay, I'm going to be greedy. I'll pick the maximum or the minimum and so on, as I described several times before. But the question is, once you do that, how do you know that your solution, your final solution, is actually optimal? It's the best one. There is no better solution. Okay? How do you know, for example, in the fractional knapsack, that the items you picked with the specific total value is the best you could pick? Maybe there is another combination of items that will yield a total sum that is bigger than what you chose. Now, so can we prove this? In the case of the fractional knapsack, yes, it's a little bit straightforward, luckily. Okay, so here is how the thinking goes. If there is a better solution, that means when you were picking from the items in front of you, you missed it. Because to be better, that means you didn't see it, or you missed it. And the question is, can you not have saw it? And the answer is no, because all the items are in front of you. There's nothing hidden. There's nothing that arrives late, for example. Now the other question is, could you have missed it? And the answer again is no, because we are given an initial set of items with known fixed weights and values, and we calculate the ratio of the price to the weight to get a value that is again constant throughout the lifetime of the problem, and we sort them by value with the most precious first. And then we start picking most precious, second most precious, third most precious, and consequently you could not have missed it. There is no way you could have missed a better solution. If it's there, it will show up in the calculations and you would have picked it. Okay? Now, it is just because of how this problem is structured. When we go to dynamic programming, you will see examples where greedy fails, because you are not actually trying the proper combination of things because of the nature of a greedy algorithm, how it works. Okay? This is what I try to highlight here in the second bullet. Okay? Suppose, by contradiction, there is a better solution. There's an item I with higher value than a chosen item J. Okay? Now, so in other words, if we substitute I with J, we get a better solution. Okay? Now, but where would that have resided? It would have resided earlier in the list of your choices. And if you're doing everything correct as we described, you must have seen it. So by contradiction, it's impossible that there would be something better that you didn't see or you saw and didn't pick. If you applied the steps we have been discussing, there is no better. all the way from the first item to the second item. This same rationale applies to minimum spanning trees and the Kruskal algorithm. When we sorted the edges from minimum, or from the smallest to the largest, what we constructed is indeed a minimum spanning tree. There is no way there could be another minimum spanning tree with a smaller total weight on the edges. Because why didn't you see it? Okay, again, if the set of edges are fixed in your graph in terms of their weight, and the set of vertices are fixed in terms of the graph structure, then there's no way you could have missed an edge that yielded, because of you missing it, that would yield later on a better solution. Okay, so here the proof is basically by contradiction. Okay, now regarding the running time of the fractional knapsack, it's n log n because of the sorting that we're doing. So if we use quick sort or merge sort, which we discussed in divide and conquer, but we didn't discuss really their performance, it's going to be n log n. Okay, that's for the sorting of the values by value, of the items by value. Okay, now after we sort them, we go over them one more time, but that's a constant. Okay, so it's n log n. I mean, it's one-time effort. It's n log n plus n, which means it's n log n. We will talk more detail about that later on in terms of the performance of the fractional knapsack and the sorting algorithms. Now, in terms of coding, how do you actually develop this? Okay, generally, coding greedy algorithms are straightforward. They're much simpler compared to divide and conquer. Divide and conquer, you could end up with a piece of code that requires some effort to digest, because often, as I mentioned also earlier, we employ recursion when we are building or constructing a divide and conquer solution in code. But with fractional knapsack or any greedy algorithm, generally, usually we would have a pass on the data to do something to the data. The simplest thing we could do is just to sort it. Okay, and then we would iterate on the data, making a pick. So you would often see it as just a simple pair of loops, which is what shows up here. Okay, there's really no sophisticated coding at all when it comes to coding a greedy algorithm, with one exception, which is the coding of obviously greedy algorithms for graphs, because there's nothing simple about graphs. So there you start seeing more complex code. Okay, but I won't show you any Kruskal implementation for the time being. The next example we're going to look at of a greedy algorithm is the Huffman coding greedy compression. Now, the idea is quite simple. You are given a file that is uncompressed, and you would like to reduce its size without changing its content. Now, you have actually seen this before, as the coming slides will show you. You have seen this before in your early computer science courses in the university, but you were not told this is greedy. Now, the idea is that we are going to become greedy in a way that makes the file size reduction happens. So let's see how that is done. The essence of Huffman encoding is like this. While we know the alphabet letters in any language, we cannot predict what words will go in any piece of text, or basically in the file we're trying to compress. So what about doing that? Inspecting this file and figuring out how many times or how much percentage of the total file each letter is being used. So I'm going to inspect the file and count the number of times A appears, or the number of times B appears, and the number of times C appears. And we'll do that for all letters in the alphabet, if we're considering English as the language used to write the content in the file. If you're doing it for Arabic, it's going to be for the Arabic letters, how many times the alif appears, how many times the ba appears, and so on. Now, what we're going to do next, and this is the essence of being greedy here, we are going to allocate a small number of bits for the letters that appear more, and a larger number of bits for the letters that appear less. So if you look here at my example, in this specific piece of text in the file I got from the file I'm trying to compress, C appeared 50%, which means half the letters in this file are C's. Obviously in this specific file I only have A, B, and C, A, B, C, and D. I don't have the other letters of English, okay, for some weird reason. But I'm just showing you that because I don't have space to actually create an example where all the letters in English are represented with statistics in the same slide. But I'm just, using here only, I'm imagining that my alphabet only has 4 letters, A, B, C, and D. So C appears 50% of the time, which means half the file content is the letter C. Now, the standard way of encoding, the non-greedy approach, is to use ASCII encoding or to use Unicode, and there the number of bits is fixed. In ASCII it's 8 bits, in Unicode it's 16 bits, okay, or 32 bits, but it's fixed. But what we do here is we become greedy in attempting to reduce the file size by allocating less number of bits to the most common letter. So we can imagine sorting the letters that appear in the file by the frequency of appearance. And the most frequent one, I will allocate 1 bit to it. When I say allocate 1 bit to it, I'm referring to the encoding system of the letters. Remember, in the ASCII code, we have a code, a binary code for every letter. So A is, like, for example, 65, but we don't write 65, we write the binary equivalent of 65. Okay? Now, so the binary equivalent of A or B or C or anything all the way till Z in the standard ASCII way of thinking is going to be 8 bits. But what I'm going to do here, I'm going to use just 1 bit to represent C, for C. And then the second one that appears frequently here is B, so I will allocate 2 bits to it. Okay? And the third is A, I will allocate 3 bits to it, and the fourth is D, I will also allocate 3 bits to it. So idea here is that let's reduce, being greedy here again means, let's reduce the file size by allocating a smaller number of bits to the most common letter and a larger number of bits to the less common letters. This is the first thing I would like you to understand. Okay? Now we will see exactly how all of this is done. I didn't tell you how the encoding actually works. I'm telling you like the merit of the idea. Now, if we can successfully do this, what's the impact? Look at the bullet at the bottom where it says the expected size. If you don't do this type of greedy approach, and your alphabet consists of 4 letters, you don't need more than 2 bits. So A is going to be 0, 0, and D, as it says in the second line, there is going to be 1, 1. So if you get a word in the file that says A, B, C, D, you're going to put 0, 0, 0, 1, 1, 0, 1, 1. And then when you try to decode it, it's going to be 0, you see 0, 0, 0, so that's an A. And when you see beside it 0, 1, that's a B. And when you see beside it 1, 0, that's a C. And when you see beside that 1, 1, that's a D. So you've put it back into the original format, which was, whoever wrote it wrote A, B, C, D. Okay? That's without any compression. But if we play with the number of bits, I will have again different bit sequences for every letter. So when I see 110, it's going to be A. When I see 10, it's going to be B, and so on. The impact of reducing the number of bits for the most common characters is shown at the last line. Okay? For the original symbols encoding, what I'm going to do is I'm going to use on average 2 bits per symbol. Okay? Now, for the Huffman encoding, the number of bits used on average is going to be reduced by 0.25. So it's going to be 1.7 bits on average. Okay? Now, this will become clearer as we see some examples, but you should get a sense of it right away by looking at the numbers in front of us. You might be wondering, perhaps, what's this 1/8, 1/4, half, and 1/8 that I'm using in the equations at the bottom? Okay? Now, I only have here 4 letters. So if I say that C is 50% of the letters, then that's a half. I will multiply it by 1 because I'm using 1 bit for C. And if I say that D is 12%, that's 1/8. I'll multiply it by the 3 bits I'm using to represent the D. The same thing for the A. And the B is 25%, that's 1/4. I'll multiply it by 2 bits because I'm going to use 2 bits for B. Okay? Where is the 2 and 3 and 1 is coming from? We will see that. But the point is, if I start varying the number of bits according to frequency, the average number of bits I'm going to use overall is going to decrease. Okay? This is what I want to explain first before we go into the details. In other words, this technique works. It should work. I mean, common sense wise, it should work. Okay? Just if you're doubtful about what I'm saying, just grab a pencil and a piece of paper and write a sequence of words all made up of A, B, C, and D, and then encode them using the original encoding, and encode them using the Huffman encoding that I'm putting here in the lecture slide, and add up the total number of bits that you use. And you will see that with the Huffman encoding, the total number of bits is less. So let's go through the greedy design process itself. What is input to you? We said that the first step you have to understand what is the input. The input here simply it's a file. Your goal is to minimize the size of the file. Your objective function is you're going to generate a binary code based on the frequency of occurrence in the given file. Okay? So you're basically generating your own encoding system. And since you're going to encode the content of the file using your encoding system, when you decode it, you also have to use your own decoding system. Just like when we use standard ASCII, we have to use it in the encoding and also in the decoding. So let's trace through the algorithm. I'm going to read it and comment. It says, scan the text to be compressed and tally or count the occurrence of all characters. Next, sort or prioritize characters based on the number of occurrences in text. I've already described these two things. When I look at the text, I will count how many times every letter appears. Next, I'm going to build what's called a Huffman coding tree based on my prioritized list. The fourth step, I'm going to perform a traversal of the tree to find out the codes I will assign to every letter. Okay? Next, I will use this to actually generate the output file. I have taught this many times before, and usually the input I get from students is that when you learned it, you've learned a simplified version of this. But this is actually the full, detailed Huffman coding that you need to be aware of. Okay, for a number of reasons. First of all, this is an example of a greedy algorithm that is doing things in a slightly sophisticated way. So compared to the knapsack, this is a little bit more involved. And second, this is a common interview question to explain how Huffman coding works. And this is actually how it really gets done. Okay? So let's go through our algorithm for a specific piece of text. And this is the text, airy eye seen near lake. And what I'm going to do is I'm going to scan this line of text. This is supposedly my file content, and I will count how many times every letter appears. So capital E appears once at the beginning of the line, small e appears 8 times, and it goes like this. K appears 1 time in the word lake, okay, and the dot appears at the end. And I have 4 spaces between the words, okay. Now, once I have built this table, this is what I'm going to do. I will create a binary tree. So this is a tree that consists of at most 2 children with the characters and frequency of each character. Okay, I will show you shortly an example of this. And what I'm going to do is I will place all my nodes in a priority queue. So I'm going to use a tree and a priority queue. Okay, and my priority queue are going to be ordered by the smaller first. So when I get from the priority queue, I am going to get the smaller value first, the smaller occurrence first, not the letter value, but the smaller occurrence. So if A appeared 1 time, and it's the only time it appears in the text, and all other letters appearing more than A, then when I dequeue from the priority queue, I should go get A first. Okay? So here is the picture. I have created a node for every letter, and these nodes will go in later to make the tree. I have put all of them in a priority queue, and it's ordered by the frequency. So as you see, capital E appeared only once, small I appeared only once, small y appeared only once. So all of these are coming at the beginning, and you see way at the end is E, small e, because it appeared 8 times. What I'm going to do afterwards is the following. I will dequeue 2 nodes from the priority queue, and that's why you see the E, the capital E and small I disappeared from the priority queue, because I have dequeued them out. And then I will create a new node that will be their parent, and in the new node I will put the sum of the frequencies. So since E was repeated once, I was repeated once, the total is 2, I will put in the new node the value 2. And then I will go and enqueue this new root, or this small tree that I just created. I will enqueue it in the priority queue. That's what you see in this picture, in this slide. The tree I have just created with the capital E and small I with their parent root node have been enqueued back into the priority queue. I will move further and repeat this step over and over again until I have only 1 node in the priority queue. So let's do that. I dequeued small y and L, and I created a parent for them, and in the parent I insert the sum of the frequencies, so it's 2, and then I'm going to go back and enqueue it in the priority queue. This is the picture now with the 2 small trees I've created inserted into the priority queue, and notice that they are being inserted in the right location. If you look at the front of the priority queue, I still have the key and dot with frequency 1, and these are the ones I'm going to get out now when I dequeue 2 more. As you see, I've dequeued the K and the dot. I create a parent for them with the sum of the frequencies, and again I'm going to enqueue it in the priority queue. So this is the picture now with the K and the dot with their parent enqueued in the priority queue. I'll continue on. Which characters are going to be dequeued? It's going to be the R and the S. So I dequeue the R and the S. It's their turn now. I create a parent for them, and in the parent I insert the sum of the frequencies. I put it back in, and as you noticed, it's going in the right location just before the small e, because now I'm talking about frequency 4. I dequeue next N and A, create a parent for them, put it back into the priority queue. This is now my picture. Notice that the number of elements in the priority queue are decreasing because I am dequeuing a pair and inserting a single node, which is the root of the pair I dequeued. So this will go on to the next step, which is again to dequeue a pair. I'm going to dequeue the tree of E and I, or capital E and I, and the tree of Y and L, and create a parent for them. Now here is the tree of capital E and I dequeued, and the tree of Y and L dequeued. I will create a new parent to join the two trees, and in the parent I will put the sum of the frequencies of the children. So it's 2 and 2, it's 4, and I put back 4 in the priority queue. This is now the picture with 4 put back into the priority queue, 4 being the root of the tree that holds E, I, Y, and L. Next I will dequeue the pair at the front of the priority queue, which is the tree for K and dot and the space. That's what you see here. So the sum of the frequencies is 4 and 2 is 6, and that's what I insert in the root, and then I put back into the priority queue. Okay? Now, time for a very important observation, which I wrote it down as a question. As you see, it says, what is happening to the characters with a low number of occurrences? Where is that? Where are the low number of occurrences, like capital E, I, Y, and L? What's going on here? Are they being pushed downward or upward? It looks like they're being pushed downward, right? So let's see why. Let's continue, and then you will see why. I go out the two subtrees of 4 and 4 that was holding R, S, N, and A. I add the frequencies and insert them back into the priority queue. This is now my picture, and I will dequeue 6 and 4 trees. So that will be my picture. I will create a new root with the sum of the frequencies. So the sum of the frequencies 4 and 6 is 10. I'll put back into the priority queue, and then now I'm going to dequeue E and the tree whose root is 8. 8 and 8 is 16. Put it back into the priority queue. Now I'm going to dequeue these two huge trees. Not really huge, but big trees. Create a new node for them. And that is the end of all of this. This is now the picture. Once I discover that in my priority queue there's only one node, so basically I should stop, because there's nothing else according to the algorithm I could do. There is no pair of nodes that I would dequeue and enqueue again. What you see here is what we can call as the accumulation of frequencies from the smallest frequency at the leaf level, going upward to the higher frequency letters, all the way till the root level. Okay? Now the question is, why are we doing all this? This is obviously a very special type of a tree that is built on a specific input. Obviously the tree will change from one input to another based on the frequencies of the letters in the content. Okay? So the question is, why are we doing this? And we are actually doing this to figure out the number of bits we are going to allocate to every letter, and what are these bits. Okay? So this is just a description of, before I show you the rest of what I have been doing. While the priority queue contains 2 or more nodes, create a new node, dequeue node, and make it left subtree, dequeue next node, make it right subtree, frequency of new node equals sum of frequency of left and right children. Enqueue the new node back into the queue. This is exactly what I was doing in the previous slides. I'm just putting them just to solidify what we have been doing. Now, again, going back to our example, we're going to dequeue from the priority queue a single node, which is the root of this tree that has the value 26. Okay? One observation here, because this is the sum of frequencies, the value that appears in the root is actually the number of letters you have. Because if I have one capital E and one small I and one small y and one small l and one small k and one dot and 4 spaces and 8 small e's and 2 small r's and 2 s's and 2 n's and 2 a's, and I'm adding up all of that, the total is 26. And you can actually count the letters in the sentence and you will see that it's 26. That's just a side observation. Here is what we're going to do with this entertaining tree. What we're going to do is we are going to create binary codes for every letter that we have in our bag of letters that we extracted from the text, based on the traversal direction in the tree. Okay? Notice that all the letters are appearing at the leaf level, which kind of makes sense because I always make these little small trees by dequeuing pairs from the priority queue, and then I create a parent for them that does not have a letter. So all the letters are actually at the leaf level. So what I'm going to do, I'm going to start from the root. Okay? If I go left, it's a 0. If I go 1, if I go right, it's a 1. Now this is why I'm actually started by saying it's a binary tree, because I want to only have options 0 and 1, because that's all what we have in the binary system. So if you're asking me, like, what's the encoding I'm going to use according to this scheme of capital E, well, you start from the root. To reach to capital E, you're going to go left, so that's a 0. Then you're going to go left again from 10 to 4, that's a 0. Then you're going to go left again from 4 to 2, that's a 0. So it's 0, 0, 0, and then you're going to go left again to the E, so that's a 0. What about the I? It's going to be 0, 0, 0, 1. Okay, you got the idea? Now, what about the Y? It's going to be 0, because going left from 26 to 10. And then another 0 to go from 10 to 4. So that's a 0, 0. And then you're going to go right to go to the 2, which is, from 4 to 2, the right child of 4. So that's a 1. And then you're going to go left to go to Y. So it's 0, 0, 1, 0. Okay? And this goes on for the rest of the letters. The really interesting part is here. What's the encoding of E? E is interesting because it is the most repeated letter. It's repeated 8 times in the text. So the greedy strategy says allocate less bits to common letters and allocate more bits to less frequent letters. Okay? Because when we placed E, we placed it in the priority queue. At the back of the priority queue, we dequeued it last, and we dequeued it the higher frequencies generally last. And because they were dequeued last, they are appearing closer to the root compared to the less frequent letters that were dequeued early on from the priority queue. That's why you see the letters that are have less frequency are way at the bottom of the tree, and the letters that have more frequency are a little bit above in the tree, and the highest frequency should be relatively close to the root, and that's what you see with the E. So let's figure out the encoding of E. So the E is, to go to the E, you're going to go from 26 to 16, so that's a 1 because you're going right, and then you're going to go from 16 to E, that's his left, so it's going to be 1 0. You see, it's only 2 bits. So the encoding for E is going to be 1 0. That's it. When you see 1 0, you know that's an E. Okay? Now, for something like A, it's going to be 1 1 1 1. Okay? And this goes on. So we're going to build a table of encoding for every letter, and in that table, every letter will be encoded with a different number of bits. And that's what you see here in this slide. For example, the space, because it appears 4 times, it has smaller number of bits compared to the N, for example, which appears 2 times only. Okay? So having this table of encoding values or encoded values will help us to compress the file. And that's what we're going to do next. I'm going to go to the text now, Erie Eyes Seen Near Lake, and for every letter I will look up in my table and figure out the bit sequence and then insert it instead of the letter. So when I see the capital E, I'm going to insert 0 0 0 0, and when I see a small I, I'm going to insert 0 0 0 1, and then when I see a small e, which appears many times, I'm going to only insert 1 0. Okay? Now, obviously we have been spending some time on this algorithm, and it looks like relatively complex. So we are, went into a side effort of creating a priority queue, and then a tree, a binary tree, and all this just to be able to do the encoding. But the essence of all of that, what's behind all of that, is that we're being greedy in optimizing or decreasing the size of the file by changing the encoding system to have the more frequent letters encoded with less bits. Okay? Now, let's see how actually this fair. Is this actually doing us any good? Okay? If you use ASCII to encode that simple line that we were looking at, it's going to take you 208 bits, which is 26 letters by 8 bits per letter. Our encoding system that we're just describing here will use 73 bits only. So that's a nice reduction in size. It's more than 50%. Okay? Now, if we just used 4 bits, now you might say, okay, why should I go through all of this? Why even should I be greedy here? Why don't I just decrease the number of bits if I don't have all the English alphabet? You see, you need 8 bits because the ASCII system has many letters and symbols. It has all the small letters, all the big letters, and a number of mathematical symbols, and all the digits from 0 to 9. Okay? Plus all the keys or all the symbols on the keyboard, whatever that is. Sometimes they're not mathematical symbols, they just use an English punctuation like rounded brackets and square brackets and angle brackets and so on. Okay? Now, you might say, okay, if I figure out I don't have all these letters, so I don't need ASCII, why don't I just use 4 bits? And yeah, sure, you're going to do it in 104 bits, which is 26 by 4. So again, that's a motivation for using something like Huffman encoding, because Huffman encoding will even beat that. It's 73 bits instead of 104. Now, one question usually I get asked, we've stopped now explaining the greedy stuff. Okay, I hope you got the idea. The question is, how do I reconstruct? Okay, now you get this 73 bits. How do you actually go about getting back the original message, which is Erie Eyes Seen Near Lake? Now, obviously, you need the tree, okay, because you cannot decode these bits without the tree that was used to generate them. Okay. Now, with the tree, it's straightforward. What you're going to do is you're going to put a pointer at the root level, and then you start scanning 1 bit at a time, going left or right until you hit a leaf. So you're going to see the first 0 in the text
So you're going to go left from 26 to 10. Then you see the next 0, so you're going to go from 10 to 4. Then you see the next 0, so you're going to go from 4 to 2. Then you see a 0, then you're going to go from 2 to the E. You find E, it's actually the letter is there, the capital E. So you insert capital E. And then you go again to the root and start again. So you're going to get 1, so you go right. Then you're going to go 0, so you go left. And then you see the small e, so you insert the small e after the capital E. Okay? So you need the tree to reconstruct the message. And obviously, this is often described in the literature as a payload of Huffman coding. Generally, it's something you add to the content. So the 73 bits are not exactly going to be what you generate in the file. You're going to generate the 73 bits plus the tree content. So you have somehow to, take this tree, serialize it, and add it to the file, so you can reconstruct the original message. Okay, so Huffman coding works when the file that you were working with is much bigger than the sizes I'm showing you here, because there is the size of the tree itself. Okay, but you still can get a major reduction in the total size, provided that your file size is not trivial. Okay. Let's see one more example. This is, again, not a trivial example. This is actually a fairly sophisticated example, even though from the look at it, it's actually working with fractions. So this is called the Egyptian fractions problem. Okay. Now, ancient Egyptians didn't write fractions, with a numerator greater than 1. Okay. They wouldn't, simply. It's just they couldn't imagine how to work the math. So they never wrote 2/7 or 5/9 or 603 divided by 912. Okay. Instead, they wrote all their fractions as a sum of unit fractions. How do we know this? We know it from the documents that were found in graves of engineers, detailing how, for example, they calculate the area of the pyramids and so on, or how they build roads and so on. So there are proofs that actually this is how they work the fractional math. Okay, remember, fractional math is actually quite advanced. You might be wondering, this sounds like retarded, but if you put yourself in like few thousand years back, our human knowledge of mathematics was not that advanced like today. So working with fractions is actually by itself is an achievement. Okay, but obviously they used a restricted set of fractions. Okay, so if they want to talk about 2 divided by 3 or 2/3, they have no notion for it. Okay, they don't talk about it that way. They would describe it as 1/3 plus 1/3. Okay, if they wanted to talk about it in a different way, they might write 1/3 plus 1/4 plus 1/12, which again boils down to 2/3. Okay. Now all of these actually boils down, as you look at the numbers, all of them adds up to 2/3. But the point is, they set some rules. The rule that they applied is that the first one is not allowed. You cannot repeat a fraction, a unit fraction. So you cannot tell me that, 2/3 is 1/3 plus 1/3. For some reason, they disallowed that. Okay. So the proper way in their system to do or to talk about or to use 2/3 was to write it like this: either 1/3 plus 1/4 plus 1/12, or 1/3 plus 1/5 plus 1/20 plus 1/12, and so on. Any one of those you could see in their documents. Okay, and that's why this system was called the Egyptian fractions system, because they used it, and it's very unique in how it works, that the numerator is always 1. So all the math was done with the numerator being 1. And when they talked about fractions, they were always going around, how can we represent this fraction using this system? Okay. And if you would like to theorize about this, obviously there is some simplicity here, because when you always put the numerator 1, then you're taking about one part from a set of known units. Okay, so 1 over 3, like you have 3 things and you take one of them. And if it's 1 over 6, then you have 6 things and you take one of them. Okay, or you're considering one of them. On 1 over 30, you have 30 things. You divide maybe a land to 30 pieces and you take 1 over them. So it's kind of simple, you know. That's why they stuck to that. Okay. Now the Egyptian fractions problem goes like this. Given any fraction, how can we generate a sequence of fractions that follow the Egyptian fraction rule, which is the numerator is always 1 and no fraction appear more than once, and in the same time the number of fractions we're using is as small as possible. Okay, so if you look at the number of ways we could write 2 over 3 from the previous slide, what we are trying to achieve is to come up with an algorithm using the greedy approach to find the first solution, which is 1 over 3 plus 1 over 4 plus 1 over 12, because this is the shortest way you can write 2 over 3. The longest way is obviously is in the last line, and we don't want that. Okay, so we want a greedy approach that minimizes the number of Egyptian fractions that will add up to a given input to us. This type of a problem is actually is not just a single problem, it's a class of problems. All of them are called the scale problems. They all related to scale, about finding values on a scale. Okay, and it appears in many different incarnations. Okay, later on in the course, for example, you will see problems, and I think you also have one of it in the practice assignment even for greedy, but I'm not sure do we still have it or not, but it's not like a big deal. You will see this problem over and over again. Giving a pass or a scale, you can think of them as alternatives, and your goal is to find specific points on the scale that are of interest, that achieve something. And I will tell you another incarnation that will sound completely different, but actually it is the same problem. You will see later on in the course problems where we tell you if you're traveling, say, between 2 cities, say from Cairo to Alexandria, and you want to find the right spots to stop on the road to take a rest, given certain constraints, like for example, you stop and take a rest at a gas station, and you have a gas station almost every, say, 10 kilometers. So the question is, which point on the scale or which point on the pass you should stop and how many times to refill your car and take a rest. You know, this is just a variation. You will see this later on, so don't really try to go into a lot of details now about this. You will see it and we'll talk about it. It's another variation of the scale problem. Generally, all scale problems are like this. You have a road or a pass or a scale or a ruler or some straight line, and you have options to choose from points on that scale or that line or that pass or that street. And when you stop somewhere, usually there's a marker. In the case of a scale, it's very straightforward. That's why I start with this problem, this incarnation of the problem. It's basically a mathematical scale, because every target point we stop at is going to be a value on the scale. Okay? So these are just few words before I go into the greedy approach here. This is not just about Egyptian fractions. This is a class of problems that are all called scale problems. Okay. Now let's go back to the Egyptian problem or the Egyptian fractions problem. What do we want? We have a scale that starts from some starting point. Since this is a numerical scale, then it starts from 0. Let's say it starts from 0. Okay, we don't have negatives here. So we're going to start from 0. And we are traveling on this scale, stopping at certain points or certain values. And we're going to add them up so that we hit our target number. Okay, this is how you think about here. The essence, this is the essence of this problem. So I'm starting at 0. and I will reach the target number. I will reach to it by picking values between 0 and the target number and adding them up to sum up to the target. Okay? So you might be wondering, like, where is the greediness here? Okay? Now here is the greedy part here. You want to jump as far as you can away from 0 and as close as you can to the target number. So imagine yourself standing at 0 and making a big jump, but we don't want to overshoot. We don't want to cross the target number. So our jump has to be big enough to get us very close to the target number, but before it. And this is really the greediness here, that I'm trying to make as big jumps as I can to reduce the number of fractions I will end up using to sum to the target number. Okay? So the question is, as I have put at the bottom picture, how to come to any specific point here. And then the next question is going to be how to come to as close a point to the target number as possible, because this is being greedy. Okay? So if you tell me, like, I want to go to 10, I want to jump to 9, and that brings me very close to 10. Okay? I'm just one value away from the 10. Now obviously with whole numbers that's easy, right? But with fractions you have to play a bit with the math to figure out how can you generate that number, a number that's very close to the target number, as close as you can ever get, knowing the target number, of course. And it has to be a systematic way. Okay? Why? Because we're going to apply it over and over again until we hit the target number. So it cannot be some random number generated. And this is often the question I get. It's good that actually I remember that. This is the question I say, okay, if I know I would like to accumulate fractions or generate fractions between 0 and target number, why don't I roll a dice? Well, first of all, this is not greedy. This is an example of a randomized algorithm where you're using a random process. The random process could throw you anywhere. It could actually generate a number for you that is close to the 0. So that's not being greedy at all. You're being quite humble, not greedy, okay? Because you're now just beside the 0. But what you want is, you want a greedy mechanism to generate a fraction that is so close to the target number. And that same greedy mechanism is repeatable, because that's what the greedy approach is all about. We are going to use some objective function and keep using it. Okay? So I hope now you're getting the essence of where this is all going and where is the greediness here. So we will need a math trick to be able to find this fraction that is very close to our target number, but before it. Now, what we only have is our target number. Okay? We have nothing else. And since we're after some systematic way of generating the fractions before the target number that add up to the target number, it's best to use the target number, okay? Instead of trying to do something else. Like I had students, for example, telling me before, why don't we try adding numbers? And if we jump after the target number, we decrease the number that we're trying to add. Like, for example, you add 100. Oh, you're above your target number, or maybe not 100 necessarily, but no, that's not really accurate. You add 1 over 50, and you find that, okay, you've crossed your target number, then try another number that will prevent you from crossing your target number. So maybe you will try 1 over 20. Okay? Now, but that's trial and error. And there's no guarantee that, first of all, you will reach to a solution. Second, even if you reach to a solution, you don't know if it's optimal or not. So it is better to actually start with the target number and try to do something with it. And this is the math trick I'm describing. So what we're going to do is, and obviously this is not a simple trick. Like, you really need to work a lot with these numbers, or to think a lot about it to reach to it. It's not something that is I would say straightforward and intuitive. Okay, so if you keep playing with the target number and you do the following, if you divide, instead of, if my target number is 11 by 12, if you divide the number reversed, I mean by reverse, the numerator becomes the denominator, and the denominator becomes the numerator. So now you divide 12 by 11. You're going to get a number that is for sure greater than 1. Okay? It's because it's going to be not necessarily greater than 1. It's going to be a whole number and some fraction. Because if you start with a fraction, which is 11 divided by 12, if you flipped it, 12 divided by 11 is going to be a whole number plus a fraction. Okay? Now, if you seal that up, you're going to get a whole number without the fraction. Okay? If you take 1 over that sealed number, it should be less than 11 divided by 12. Now, I know that by now you're probably rolling your eyes and it's like, how would you know that? Well, it's actually related to number theory, basically. Okay? When you divide a big number by a small number, and you take, I'm really stating myself again here but in a different way, and you take the ceiling of that, and you take 1 over the ceiling of that, that must be less than the initial fraction you start with. Okay? So this is actually how we will get a systematic way of generating fractions that are Egyptian, 1 over something, and that are below or less than my target. Okay? So this is, again, the same example, but with a little bit of text so that you consolidate the idea. What I'm going to do is, I'm going to flip the fraction I'm working with, seal up the division, and then put the quotient, or the result of the division, with the ceiling in the denominator. And the numerator will remain 1. And I will repeatedly do that until I am done. So I started with 11 divided by 12. I will flip it, it's 12 divided by 11. I will seal it up, it will end up being a 2, a whole number. Then I will say that my first part in the solution, my first part of the solution is 1 over 2, which is an Egyptian fraction. Now, I will subtract the half, the 1 over 2, from the fraction I'm trying to target, which is 11 divided by 12. I will get 5 divided by 12. Now, the problem becomes, I would like now to solve 5 divided by 12. So I will divide 12 by 5, seal it up, it's going to be 3. Then I will use 1 over 3 as my second Egyptian fraction that is part of my solution. Then I subtract that from 5 by 12, I get 1 over 12. I am lucky now because I got right away an Egyptian fraction. So the answer is the minimum number of Egyptian fractions I could use is 3 to represent 11 by 12, and it is half and a third and 1 over 12. Now let's conclude by talking about the greedy method. Okay? When to use it? When to use a greedy method? Okay? Now, we have a nice term that we use to qualify problems for using greedy. If a problem has what's called the greedy choice, what do I mean by a greedy choice? I mean that a globally optimal solution, which is the bullet I've written here, can always be found by a series of local improvements from a starting configuration. Okay? Now, if a problem supports the greedy choice, then sure, go ahead and use a greedy method, come up with a greedy algorithm, and you will get an optimal solution. You could still use, and this also happens, use a greedy approach to a problem that you know that does not have the greedy choice. So why are you doing that? Well, at least you're going to get a solution, but it's not optimal. Okay? But the ones that will give you optimal solution, where you know that every decision you make is taking you towards a globally optimal solution. Okay? This appeared several times in counting money, in the fractional knapsack, in the Kruskal minimum spanning tree. Every time we made a decision, we know that there is no way there could be a better decision. Okay? We are doing the best that can ever be done. But obviously not all problems are like that. Okay? For example, we looked in the scheduling problem, the scheduling jobs, and we noticed that whether we pick the minimum or the maximum, we were not achieving an optimal solution. If you go back to the lecture slides, you will notice that the best solution I believe we reached to was 35 minutes, and using dynamic programming you can get 34 minutes, so you can get a better solution. Okay? So in scheduling jobs, the greedy choice property does not hold. Okay? But however, in the Kruskal algorithm, it does hold. In the fractional knapsack, it does hold. Okay? So, the greedy choice property does not, it's not a must that it will exist in all problems given to you. But if you are after an optimal solution, then before choosing greedy as the approach, you should check for greedy choice. Okay? If you're after an optimal solution. If you're after any solution, that's a solution, then yeah, go ahead and use greedy. Okay? But if you're after an optimal solution, and in many cases actually we will be, okay? That's why, there's research and innovation in algorithm design, because we're after the best possible ever optimal solution, or the best possible solution, and consequently, you need to check for the greedy choice in most cases before applying a greedy approach. These are the references for today's lecture. I have 2 textbooks that cover greedy algorithm design. I would like you to read both of them. I would advise to start with the Goodrich and Tamassia textbook, and then go and read Corman, because as I mentioned in the first lecture, Corman is a little bit more advanced in the writing style and in the kind of problems they cover, while Goodrich and Tamassia is slightly simpler and straightforward to read. So start with Goodrich and Tamassia, and then go and read Corman and the other guy's textbook. Okay? I have also put references for the fractional knapsack and the task scheduling from Goodrich and Tamassia. It's well explained there. And for the Huffman coding, I also I'm including 2 references, one for the Corman textbook and another one for Goodrich and Tamassia, and also the same thing for Kruskal. And you can download the text following the links I'm providing.